Hello, everyone, and welcome to another decisions training video. We are going to be going over identifying redundancy and optimizing solutions within the decisions platform. So, we are going to be focusing on this redundancy part at the beginning, and we're going to start with identifying what redundancy is. After we've defined it, I'm going to go into classifying redundancy and then identifying it within the platform itself. Then we'll go over how to fix it. And I'll give some demos on that so you can see some examples of redundancy occurring inside of different project builds. So, first thing is, what is redundancy? When you are developing a program, redundancy refers to the unnecessary repetition of code, logic, or data. The potential consequences of this redundancy can be inefficiency. You could have a program that runs as expected, but not as quickly as expected. You could have increased costs. If you are saving more to the database than you need to, you're paying for that space. If you're making more API calls than you need to, you're paying for those services. The other thing that it can cause is potential errors in your code. If you have multiple sections of the same logic over and over again, and you have to update each one manually for any new process being added, there's a higher likelihood of errors occurring in that update process. So, we're going to help you identify these types of redundancy to avoid these issues. Let me give you an example of a redundancy. Let's say that you are going to an ATM and you want to insert $100 into the ATM into your checking account and then also withdraw $40 from your checking account. This is a redundant process and could have just been avoided by adding $60 to the checking account without having to perform multiple transactions. Now, something to keep in mind is that there are cases where things may seem like redundancies, but they are not. For example, if you are inserting $100 into your checking account, but then withdrawing 40 from savings, then these would be two separate processes. Perhaps you transfer money over and withdraw, but regardless, you're still performing two actions. This cannot be condensed into one. Another thing that might occur is suppose it was a $100 bill. Then you would not have the option to insert just $60 of that $100 bill. So it is important to be able to recognize redundancy, but also to be able to recognize what is not a redundancy. So, with that being said, let's go into the types of redundancies that you can encounter. The first kind is a code redundancy. This occurs when you are recreating the same or very similar process in multiple times within a program. All right. Or in our case, our flow. So in this particular image, you can see that we are fetching recipes. We are then going to loop through each recipe and then determine the last access date. If the last access date is within 90 days, then we set the entity state to active and then add it to an active list. If it is not within 90 days, then we set it to an archive and then add it to an archive list. In order to identify these kinds of redundancies, you want to be able to ask yourself, am I repeating any steps in my flow? Or am I trying to perform the same action multiple times? If so, these can be questions that may lead you to find processes that are redundant in your particular setup. Another type of redundancy is called a data redundancy. When you are storing the same data in multiple places, this can lead to inconsistency and inefficiency when trying to select, update, or delete that data. For example, in this image right here, you can see that we are saving date of birth and age. Why would you need to save both if you would be able to calculate one from the other? There may be cases where you need both, and if it is clearly defined that you need both, then it's not a redundancy. But you don't want to make that assumption. You want to identify these particular decisions that you're making critically and determine if these savings are necessary. The questions you want to ask during this are: am I saving the same data to multiple tables or columns? Or am I storing the same data in multiple variables? The last kind of redundancy that we're going to be covering in this lesson is logic redundancy. This is the use of more operations than necessary to produce the same result. So, for example, in this particular rule here, we have an either or condition where we're checking if the number is equal to 42 or if the number is less than 50. Well, if a number is equal to 42, then it is certainly less than 50. We don't need both of these conditions. So we can eliminate the first one and just use the second condition in this particular setup. Questions you want to ask yourself to identify these kinds of redundancies are: am I checking the same condition multiple times? Or am I using the most efficient steps? So now that we've covered those kinds of redundancy, I want to go into how to fix these. The first option to try and address redundancy is utilizing subflows. If you are using the same process multiple times within your decisions flow, you may want to consider using a subflow so that this logic can be consolidated and act as a singular step within your flow instead of rebuilding the logic every time you need it. Another thing you'll want to consider is if you're using the most efficient steps. Let me give you an example of this one. Let's say that you have a process where you want to be able to change the assignment of a user. That is, a user has been assigned a task, and somewhere in your process, someone can override that assignment and send it to someone else. Well, one option you might consider is using the two internal service steps: add assignment for user and remove assignment for user. Therefore, adding the assignment to someone else and then taking the assignment away from the previous owner. This would function. However, there is a simpler way to do this with a singular step called change assignment within that same assignment service. This is an example of reducing redundancy that occurs from not using the most optimal steps for your particular build. Another thing you may wish to consider is reorganizing your flow logic. You want to check if your redundancy is a result of an order of flow operations. Fourthly, you want to limit your API calls. If multiple API calls are made to the same service, see if that data can be retrieved or sent in less calls. If you are calling the same service multiple times for selective operations to pull information into decisions, see if you can get all that information in one call instead of calling a service multiple times, saving you both time and money. Limit your database calls. If you are performing multiple operations to the database, do they need to be separate? Can you use a batch insert instead create user defined type? Is it necessary for each update to occur individually, or can they all occur at once? These are questions that are important to ask in order to optimize the run of your flow. And then lastly, you can normalize the database. This is not a decisions functionality. Rather, this is a process by which you can reduce data redundancy within your database by organizing how information is stored according to three key principles. I'm not going to go into this right now, as that is a bit beyond the scope of this course. So now that I have mentioned these, I'm going to give you some examples where we can identify some redundancies that are occurring and show you how to fix them. All right, here I am inside of my decisions environment. I've got two examples I'm going to be going over here. So the first one right here, we're going to jump into. And what this flow is going to do is going to take in the weight, the quantity, and the item name of a good, and it is going to determine whether or not it is going to calculate the price by its weight or by its quantity. The way it determines this is if one of these is 0, then it will use the other one to calculate. It runs a truth table to check the prices for things that are measured in weight, or a truth table to measure the price for the things that are measured in quantity. And then it multiplies that price per item by its total weight or by its total quantity and outputs that total. So, asking some of our questions before, do we have any repeated processes here? Well, we have something that's very similar, right? We're running a truth table, and then we're going to multiply the output of that truth table by one of our inputs here. But can we make this more efficient? This might be a type of redundancy. But these truth tables are different, so how could we handle that? Well, we could still turn this into a subflow, and I'll show you exactly how. So right here, I have already configured the logic, and I've put each one of these inside of its own subflow, and we pass in a weight or quantity, an item name, and a truth table ID. So what happens now is it determines if it is going to use weight or quantity, just like before. If it is quantity, it will pass that into this variable that captures either one. If it is weight, same way, this variable that captures either one. And we can determine which one it gets passed into by the true or the false path. The truth table ID will determine which truth table we're going to run. So this is the exact same process. These are not two different subflows. This is the exact same subflow. I've just changed what my inputs are to it. And now I can run the same process for both. This also allows for more scalability. If I wanted to add another way to calculate a total price, then I can just create another truth table, pass in its ID into my subflow, and I don't have to recreate the whole process anymore. This was an example of a code redundancy where we are reusing similar or identical elements over and over in our process or on multiple outcomes here. We can configure one select section of flow steps and call them as a subflow instead to execute this process. Let's go over a different kind of redundancy now. So here we have a way to calculate Euler's number. What we'll do is we will take 1 over the factorial of each repeated fraction that is getting added to each other for as many as we determine, n times. So what this will allow us to do is approximate it to the nth degree, okay? So when I debug this, if I were to run this 5 times, you'll see that I initialize the sum. For this amount of degrees, I will initialize a variable. I will add 1 to them so that I can pass a 1 in for the number of iterations instead of a 0. I'm going to do the same thing here when I multiply my numbers because factorial is this number times each previous integer before it, right? So this will give us this factorial right here. It will take the reciprocal, so 1 over that factorial, and then we add the fractions. And this is going to allow us to build this sum of these repeated numbers until our last run of this, which is going to get us somewhat close to the number, right? So our output right here is going to give us 2.716 repeating, okay? So we should ask ourselves, are there any repeated steps? Well, in this case, we are running things through a loop, right? So we should be aware of what our process is doing and understand if we need these loops at all. Well, we are going to have to iterate through each number and perform some calculations, right? So we're going to need at least one loop. However, if you notice in this factorial calculator, by the time we get to the 20th one, we're going through this 5 times, right? We've already gone through this multiple other times before this. So we should consider that we might be able to take each factorial as it's calculated and then add it before trying to recalculate every number up to the one that we need and then just add that number and go through the whole process again for the number after it. So this is an example of a logical redundancy. We are running this over and over again, and in some of our outputs, we are getting some of these numbers that we need before we even reach that number. So we are wasting these calculations, whereas we could be running something like this. This still initializes the variables. This one is still going to be a loop that will add 1, multiply the numbers, take the reciprocal, and then add it to the total. This is important because this means that this will be for 1 factorial, 1 over 1 factorial gets added, 1 over 2 factorial gets added, 1 over 3 factorial, and then so on to the nth time. So if I were to debug this, With 5 as our example again, you'll see our output is identical to the previous one, but we don't have to run a loop inside of a loop anymore. So, this is an example of a logical redundancy where you are going through the same steps that you do not need to utilize in order to get your output. You can reuse the same runs from before and add each of those individually in the case of our formula here. So, when you are building a project, ask these questions along the way and try to determine if you are building your project in the most efficient way possible. And if not, what can be done to eliminate those redundancies. Thank you very much for watching. Hope this helped.